Hi all. Now we can start our third semester. I think Sabnamis had already started with your first chapter. Now I like to start with our fourth chapter, which is oscillations and waves. In this, we have to study the topic SHM, that is simple harmonic motion and equation of SHM, and some examples like oscillations of simple pendulum, loaded spring, etc. Then we have to study damped harmonic oscillator. Then finally we have to study regarding with waves, that is equation for plane progressive wave and energy density and pressure variation in plane waves. So let us start our chapter. We all are familiar with some repeated motion in our neighborhood. That is a motion which repeat itself after regular interval of time. Such motions are coming under simple harmonic motion or periodic motion or oscillatory motion. We can categorize them periodic motion, oscillatory motion, and simple harmonic motion, etc. Some examples are motion of a swing, that is that motion repeats after regular interval of time, but we can see its amplitude decreasing. Such motions are called damped oscillation or damped motions. So first of all, discuss with periodic motion. That is, as we know, a motion which repeat after a regular interval of time. That time is called period. Any motion which repeat after regular interval of time is called periodic motion. So mathematically we can represent that motion by a function. Such function should be f of t plus capital T equal to f of t. That is, this function should repeat after that period capital T, where capital T is called period. Examples for such functions are sine theta. We know that sine of theta plus 2 and pi is equal to sine theta. Okay. Such functions can be used to represent such a periodic motion. Okay. So any motion which repeat itself after regular interval of time is called periodic motion. We can represent such a motion by this equation. Okay, these are some examples. Motion of Earth around Sun. We know that it takes 365 days, and motion of Earth around about its own axis will take 24 hours. Okay. Then motion of pendulum, vertical oscillations of loaded spring, etc. are some examples for periodic motion. Now let us take oscillatory motion. In this, there should be a point of equilibrium about which the motion executed. A motion in which the body moves to and fro repeatedly about its fixed point and repeat this motion after a regular interval of time. Such motions are called oscillatory motion. Okay, so there is a point of equilibrium or point about which that motion is executing. So oscillatory motion can be split up into periodic plus to and fro. That is, periodic motion plus to and fro motion about a fixed point can be coming under oscillatory motion. Examples are motion of a pendulum, vertical oscillations of loaded spring, etc. are some motion. In these, the motion repeat, but also there is a to and fro motion about the point of equilibrium. So oscillatory motions can be expressed in terms of sine or cosine function or their combination. The simplest form is sine function, because sine of theta plus 2 pi n equal to sine theta, cos of theta plus 2 pi n equal to cos theta. Such functions are called simple harmonic motion. So any function which can be represented in terms of the simple harmonic function is called simple harmonic motion. Okay, an oscillation which can be expressed in terms of a simple harmonic function is called simple harmonic motion, and a system executing such motions are called simple harmonic oscillator. Complicated oscillation can be treated as such harmonic oscillations that may be damped or undamped case. So we can resolve that into one or more simple harmonic motion. As the complexity increases, the complexity of the function that may be a combination of one or two harmonic function. In simple case, we can represent a simple harmonic motion using only one sign of particular function. Okay, let us move to simple harmonic motion. In simple harmonic motion, the force at a particular point is proportional to displacement from that fixed point. That is the criteria for a motion to fall under simple harmonic motion. Just take an example. When you are on a swing, when it is at the resting point, we doesn't feel any force. Okay, at the equilibrium point of a swing, when you are sitting on that swing, you doesn't feel any force, and you doesn't feel any force at the point of equilibrium. When you are at one extreme end of the swing, the force is maximum and you feel some uncomfortness when that amplitude is much maximum. Okay, then because at that point force is maximum, that force is pulling you towards the equilibrium point. Okay, when that amplitude is decreasing, your force is decreasing, so you feel some comfortness, and at the point of equilibrium, because of inertia, that overshoot that equilibrium point and you can go to another end. Okay, such motions are coming under simple harmonic motion, that is to and fro motion or to and fro periodic motion plus a force, restoring force on that particle is proportional to displacement from fixed point. That is, a particle said to execute simple harmonic motion when it moves to and fro periodically in such a way that at any instant restoring force acting on the particle is proportional to displacement from a fixed point and is always directed towards that point. Such motions are called simple harmonic motion. Examples are pendulum, bob attached to a spring, etc. etc. Now, in order to derive expression for a simple harmonic motion, consider a particle of mass m attached to a spring of negligible mass. When that mass is displaced slightly at distance x, then we know that the restoring force is proportional to minus x. Let us take this one. Here mass of this bob is m. Then once it is compressed, then a restoring force will develop, and force is proportional to minus x. That force try to pull the spring towards the equilibrium point. Because of inertia at this point, it will overshoot the equilibrium point and that will expand. At this point also, restoring force is maximum and that force try to pull it to equilibrium point. This point also that overshoot, and this compression and relaxation will repeat itself after interval of time and it form a simple harmonic motion. Okay, we can represent its position by such a graph. Okay, now we have to derive the equation for the simple harmonic motion. The only quantity we know is the restoring force F is proportional to minus x, where x is the displacement from the equilibrium point. Here, this is the equilibrium point where M balances. Okay, so this compression or relaxation executes between the equilibrium points. Okay, so we know that F is equal to M into A mass into acceleration, that is M into d square x by dt square is proportional to minus x. When we replace this proportionality constant, we get M into d square x by dt square is equal to minus kx, where k is the proportionality constant. So on replacing this equation, d square x by dt square plus k by m x equal to 0. Let k by m be omega square, where omega is known as angular frequency. So d square x by dt square plus omega square x equal to 0, where omega is equal to root of k by m. So period of oscillation, we know that equal to pi by omega. So 2 pi by root k by m, that is equal to 2 pi into m by k. Frequency equal to 1 by t, that equal to omega by 2 pi. And so this period is called the time interval in which that motion repeats. And frequency is the number of times that motion repeat in a 1 second. Okay. So all of you do this example. The equation of a simple harmonic oscillator is given by d square x by dt square is equal, d square x by dt square plus 625x equal to 0. Find the period and frequency of the oscillation. All of you prepare note for this discussed topic and do this problem and submit in your Google Classroom. Okay, so we discussed what are periodic motion, oscillatory motion, simple harmonic motion, and we derived the equation for SHM, that is simple harmonic motion. Okay.